there. One of the most important aspects of how Earth enables life to thrive is that it has a magnetic field. Now, you may have wondered whether or not planets outside the solar system, namely extrasolar planets, if they are capable of having magnetic fields in order to have conditions that are pretty good habitability. That's what my talk is going to be about. I'm going to try and answer the question whether or not they can actually have magnetic fields as well. Spoiler, they can, but they're pretty strange and not quite what you might expect. I'm Mahesh Herath, and I'm at McGill University, and I am doing my research on terrestrial exoplanet interiors. So let me quickly just start sharing my screen so that we can start the presentation. Oh, there we go. Okay, so my talk is going to be about how exoplanet magnetic fields can be modeled, namely for terrestrial exoplanets, and what they reveal about certain kinds of planets that we are looking at. Now, the importance of geomagnetism, as I mentioned earlier, is that it's important as a protecting agent against stellar radiation, so that it protects the atmosphere from being eroded away from the from the radiation that is being emitted from their host star. And as an example, Mars lost its magnetic field about 4 billion years ago, and its atmosphere had faced depletion since then. So I'm looking at exoplanetary systems where they're actually orbiting much closer to their host star, so they are at a severe risk of being exposed to things like flares. So it's very important that they actually have magnetic field. Now, if I just quickly talk about what planetary interiors are, they are pretty much subdivided into several different layers in each planet. Now, if you take our own solar system, each terrestrial planet in the solar system has a core, a mantle, and a crust. But for exoplanets, it's going to be much different because terrestrial exoplanets actually have a lot of something. For say, for example, a planet that's much more massive than the Earth, it wouldn't have the same kind of interior that you would expect for something like Earth or Venus, for example, which is something we had to take into account. As you can see over here, so if you take Earth's structure, for example, we have an inner core that is made of solid iron, an outer core which is also made of iron, but actually liquid. Then you have a lower mantle, an upper mantle, and then a crust. We actually assume that this basic structure is going to be preserved for pretty much every kind of terrestrial planet that we're modeling. And I would say that is a very fair assumption. So the way the magnetic field is generated is that when the solid inner core is forming, when it keeps solidifying, it releases light elements into the outer fluidic core. And when this is happening, so when these light elements are being released, it's actually creating what we call buoyancy-driven convection. And this buoyancy-driven convection is what leads to the generation of a magnetic field, when the buoyancy-driven convection actually drives electrical currents in the conducting liquid core. And that's how you actually start getting magnetic fields overall in practically any planet that can do that. And that's what we're going to look at. That's what we are going to look at. Can exoplanets, terrestrial exoplanets of many different masses, be able to do that? So the way we do it is we first create an interior structure model. We get the parameters of the planet, what the core temperature is, how big the core is, where the mantle starts and where it ends. Then we take it and we feed it onto a thermal model, which looks at how the heat inside the planet changes over time. And then we use the heat changing and the entropy changes that happen inside to determine whether or not a magnetic field can happen. And if it does, how strong is it? So first of all, I'll just tell you about the interior structure model. So we start the interior structure model with an equation of state. An equation of state pretty much tells you how the thermoelastic properties of a material changes depending on the pressure and temperature at a certain point on the planet. So that's what we're going to do over here. We take an equation of state, And as you can see over here, we use three different equations of state: one for the inner core, one for the outer core, and one for the entire mantle. And these are the most up-to-date equations of state that we have. So it's going to be pretty useful when we actually doing the model here. And we actually adjust the thermoelastic data depending on the phase changes that happen inside the planet. And we also look at the elemental abundance, and pretty much the elemental abundance here is that we look at magnesium, aluminium, silicon, iron, oxygen, calcium, and we put all of them together, and we actually, that's the composition we're using. So we are essentially assuming it's a Earth composition in all these terrestrial planets. And then what we do is we take five differential equations given here for pressure, gravity, mass conservation, temperature, adiabat, and the conducting gradient. And we integrate them using a fourth order Runge-Kutta algorithm. And when we do that, we can get profiles for gravity, pressure, density, and of course, temperature inside the planet. So if you take a look here, we start from the core, model the core, and then we put the lower mantle above that, then the upper mantle, and then we go to the crust at last, and we have a planet. So now I'll quickly look at tell you about the thermal model. So the thermal model essentially takes the parameters that we determine based on the interior structure model, and then we put it in and we feed it into this thermal model. So it's pretty much looks at how quickly the mantle and the core cools over time, and how it conserves the amount of energy that's available for generating a magnetic field. So what we do is we actually balance all the different energies that you can find inside the core, namely the heat generated from secular cooling, heat generated from the gravity redistribution that happens when a core is solidifying, and the heat lost by general cooling of the liquid outer core. And then use the entropy balance, which is essentially the analogous to what we look at heat. And then we use that entropy balance to find out the convective power of the core. So the energy balance essentially tells us how the core and the mantle cool over time. And the condition and the entropy balance tells us how much power is left in the core to drive that dynamo. So if we look at the temperature at one point, we change it, then we look at it again. Is the temperature enough to have enough power in the core to drive a dynamo? And then we go on, and at the same time, we keep growing the core slowly over time. And as the core grows, we just keep checking, is there enough power now? Yes, keep going. Is there enough power now? Yes, keep going. Is there power now? No, no more power. That means the dynamo stops working. And it's at that point we stop our integration of the model. And that's when we find out that it tells us how long the magnetic field would last and how strong it is. Yeah, so these are the equations, just more gory details on the equations that are being used for heat balancing, and of course, the entropy balancing. So you can take a look at this if you want later on when I upload the presentation as a whole. And if we look at the magnetic fields that are generated from them, we essentially use analytical equations used from the Aubert and Christiansen paper from 2006 and 2009. And we are looking at, and the first thing we do is we look at the Rossby number. The Rossby number tells us whether or not the magnetic field is dipolar or multipolar. So the threshold between a dipolar field and a multipolar field is you need to have a Rossby number of 0.1. If it's higher than 0.1, it's going to be a multipolar field. If it's less than 0.1, it's going to be a dipolar field. So we would prefer to have a dipolar field because dipolar fields actually are more predictive of planetary atmospheres than multipolar fields. And of course, after knowing the kind of field we have, we can actually calculate the planetary surface magnetic field, which is pretty much what we need. And if I show some preliminary results, so these are some tests for the Earth, and it pretty much recreates the kind of modern day magnetic field strength that the Earth has over a course of about 4.5 billion years, with a Rossby number that's very close to 0.1, but not quite there. So it's just tethering on the edge of whether or not it's going to be multipolar or dipolar. But here's the thing, Earth has a core mass fraction, and just to be clear, core mass fraction means how much of the core's mass, the planet's mass, can be found in the core. So Earth has a core mass fraction, CMF, of 32%. That means 32% of Earth's mass can be found in the core. Now, you get a strong magnetic field for a 32% core mass fraction, but what happens if we increase it to 50%? If we increase it to 50%, it actually kind of shuts down the dynamo in that particular planet on Earth. So as you can see, change in the core mass fraction can actually alter how well a magnetic field can be generated. But now if you look at some exoplanet results over here, you can see that the kind of fields you get with changing mass. So you have 2 Earth mass, 3 Earth mass, and 4 Earth mass. And as you can see over here, for 2 Earth mass planets, you can get pretty strong magnetic field even for a 32% core mass fraction. But when you get to higher core mass fractions, it becomes more damped compared to what you get for the other core mass fractions, mainly because when you get to bigger core mass fractions, there's more viscosity between the core mantle boundary. So that's one reason. And for example, if you change the thermal conductivity, it can actually significantly alter the kind of magnetic fields we get. For example, if you get for a 2 Earth mass planet, you can have a CMF of 32%, but if you change the thermal conductivity at the lower mantle, for example, in the top panel, you can see that there's a dipolar magnetic field. And in the bottom panel, the reason why there's a jump here is that after a while, it actually switches from a dipolar field to a multipolar field. So slight changes in the thermal conductivity actually can have strong effects on the kind of magnetic fields that you get. And same over here. So on the left, you have, so if you have a thermal conductivity that's low, say 12 watts per meter per Kelvin for a 4 Earth mass planet, it might not have a field. But if you change it to a higher value thermal conductivity, that means there's more thermal energy in the lower mantle. Thereby, it means it might have a magnetic field, even one that can last about 10 billion years, which is actually a very long time. But yeah, but sometimes, no matter how much you change thermal conductivity, you just can't get a strong magnetic field in the planet. Like you can see over here that the En over here is the entropy that you get from secular cooling and gravity-driven buoyancy, whereas Ek is the entropy change that happens because of thermal conduction. So En always has to be higher than Ek for a dynamo to keep going. And what you can see over here is that even when for some kinds of planets, even if you increase the thermal conductivity, it's just not enough to help the dynamo along. And if I just take a look at like mention some of the aspects of the modeling that we have to pay attention to, some of the things that we have to look at are parameters such as the thermal conduction in the lower mantle, the thickness of the core mantle boundary, and the initial temperature of the core. So these are all uncertain values, and this is still a work in progress. So we need to still test the model extensively to see if the results we have can be reliable enough to keep working on. And one thing we can do is we can test it for Mars, so that because there are Martian rocks that can be looked at to see if the paleomagnetism that our model predicts can be found in paleo Martian rocks. That's your word. Sorry, but yeah, so this is just some things we have to pay attention to further down the line, and that's what I'll be doing. I'll be working more into looking at how these models can be improved to look at whether exoplanets can have the kinds of magnetic fields that terrestrial exoplanets can have. But yeah, so that pretty much wraps up my talk. And thank you so much for listening. And hopefully it caught your interest on the kinds of about planetary interiors and planetary magnetic fields, and I hope it piqued your interest into it as well. So thank you so much. And I will hope to get questions from you at some point.